Welcome to this video. In this video we are going to discuss about integrator. An integrator is nothing but in which we obtain integrated waveform at the output. We obtain an integrated waveform of the input at the output of the circuit. Such an integrated circuit is obtained by using the basic inverting amplifier, in which the feedback resistor RF is replaced by a capacitor CF. Integrator is a circuit which will provide an integrated waveform of the input at the output of the amplifier. We can obtain an integrated circuit simply by using the basic inverting amplifier, in which the feedback resistor RF is replaced by a capacitor CF by using Kirchhoff's current law at the node V2. And the basic circuit of the integrator is shown in the figure. We can obtain the output, an expression for the output voltage by using the Kirchhoff's current law at the node V2. By using the current law, we can write I1 equal to input current I1 equal to IB plus IF, but by the assumption that no current will flow into the operational amplifier, we can choose IB as 0 or negligibly small. So I1 equal to I in IF. From the figure we can write I1 as V in minus V2 divided by R1, but by the concept of virtual ground. Since the non-inverting terminal is grounded, same potential will exist at the node V2. So V1 equal to V2 equal to 0. So I1 equal to V in divided by R. Similarly, the current flowing through the capacitor IF will be equal to C into dVc divided by dt, where Vc is the voltage across the capacitor CF. We can write the voltage across the capacitor Vc as V2. We can write it as IF equal to C into d by dt of CF, feedback capacitor CF. CF into d by dt of V2 minus VO, but we know that V2 equal to 0, so IF equal to CF into d by minus CF dVO by dt. The output voltage, so IF equal to minus CF into dVO by dt. So we can substitute the values of I1 and IF in this equation. So we obtain V in by R. V in by R1. V in by R1 equal to minus CF dVO by dt. We will obtain the output voltage by integrating this equation. So VO equal to minus 1 by R1 CF integral V in dt plus a constant of integration C. So the output voltage VO equal to minus 1 by R1 CF integral V in dt. This is the output of the circuit shown in the figure. Here VO equal to minus 1 by R1 CF integral V in dt. So the output is the integral of the input voltage. The constant C is the integration constant and is proportional to the value of the output voltage VO at a t equal to 0 seconds. This figure shows the output waveform of a basic integrator circuit. If the input voltage is a square wave, if it is a square wave, the output will be a triangular wave, and if it is a sine wave, the output will be a cosine wave, and its polarity will be changed because it is in the it is in the inverting configuration, so its polarity will be changed. In this case, it is a sine wave. and the output is completely negative. Here also it is a square wave, the output is a triangular wave and its polarity is inverted. In this figure, this figure shows the basic frequency response of basic integrator circuit. In this figure, we can define a frequency FB as the frequency at which the gain is 0 dB or the unit gain. In dB, it is 0, or when we say in usual case, it can be 1 hertz. If its gain is 1, its gain in decibel will be 0. So we can define a frequency FB as the frequency at which the gain in decibel is 0. So we can obtain an expression for that frequency FB as FB equal to 1 by 2 pi R1 CF. At present, we have no need to derive this expression, just an equation for this frequency FB equal to 1 by 2 pi R1 CF. Similarly, we can define another frequency FA as the frequency at which the gain decreases at a rate of 20 dB per decade. And up to this frequency FA, the gain remains a constant. The gain continues to be a constant, and at a particular frequency it begins to decrease at a rate of 20 dB per decade. That frequency, we can obtain an expression for that frequency as FA equal to 1 by 2 pi RF into CF. It depends on the resistor value RF. Here RF is nothing but at low frequency, in order to avoid the low frequency roll-off problems as well as to give stability to the circuit, we can add an extra resistance RF in the RF parallel to the capacitor CF in the feedback circuit. This is the case of a practical integrator. In practical integrator, we usually use a resistor RF parallel to the capacitor CF in order to avoid the stability problems as well as the low frequency roll-off problems. So, in that case, the frequency at which the gain begins to decrease at a rate of 20 dB per decade, we will have an expression like FA equal to 1 by 2 pi RF CF. Here, the frequency depends on the resistor at the feedback network. The gain at the high frequency, or the frequency at which the gain becomes unity or becomes 0 dB, can be written as FB equal to 1 by 2 pi R1 CF. Here it depends on the resistor R1, that is the resistor connected to the input resistance of the circuit.